In this video, we're going to go ahead and start the next little unit, which is called transcendental functions. So pretty much everything we've been doing this year so far has been, okay, there goes the bells at starting point, thank you. No students here, but that's okay. Everything we've been doing so far has been algebraic. So things you could solve with algebra, typically multiplication, division, addition, subtraction, raising something to the third power, taking a square root, etc., etc., etc. Stuff that you can solve with algebra, those equations are considered algebraic, right? But things that you can't solve by using algebra, they're non-algebraic. And another word for non-algebraic is transcendental. Now, we've actually been doing some transcendental functions all year, right? The trig functions are transcendental because you can't solve something like sine of x equals 1/2. You can't solve that by using algebra. You have to use trigonometry, right? So since trigonometry is non-algebraic, we could also call that a transcendental function. So we've done some transcendentals already this year, right? But just the 6 basic trig functions. This notes packet is going to help us to learn how to do calculus with more types of functions, and specifically some of these transcendental, i.e. non-algebraic functions. We're going to do the natural logs first. Then we'll move on to exponentials. And then once we're done with the exponentials, then we'll look at doing derivatives of inverse trig functions. Okay, so the goal of this packet is, now that we've kind of got all of our different calculus skills, we know how to take a derivative and the applications of it. We know how to take an integral and some of the applications of them. Now we're just going to learn how to apply those skills to new types of functions into these transcendentals, starting with the natural logs and then the other logs first. Okay, so it's going to start off, each little section has a little bit of pre-cal review at the beginning of it. Now, some of y'all may have not hit this as in-depth as usual because of, whatever circumstances last year. So we're going to do a little bit of pre-cal review, and then we'll learn how to take the derivative of these natural logs, and then hopefully we'll be okay with this stuff today. All right, the stuff at the top is kind of just some basic information for you. E is a constant, kind of like pi. And you should know that it's about 2.7. We have the exponential function, y equals e to the x. We have the natural log function, which looks like this, y equals ln of x. And we know those two things are inverses of each other. So here we see the graph of y equals x. Since those other two functions, the exponential and the natural log, since they are reflections of each other over that line y equals x, that's visual confirmation that we know they're inverses of each other. Remember, inverses, they switch to x's and the y's, so the domain and the range swap places. The domain of the exponential is the range of the natural log, and vice versa, right? They're inverses of each other. That's great. So some basic practice. We're caring mostly about the natural logs today, and here's our basic parent function, which would have a vertical asymptote at the y-axis. You cannot have a 0 inside of a log, and you also cannot have anything negative inside of a log. So there are some domain restrictions for these natural logs. Cannot be 0, but it could be anything bigger than 0. Now, if you have something like ln of 1/2, 1/2 is between 0 and 1, so then the graph at that point would be negative. So ln of 1/2 would be some negative number. But that's okay. Ln of 1 gives us 0. That's where the natural log graph has its x-intercept. And then anything past 1 gives me a positive output. And ln of e, the 2.7, whatever value, ln of e gives us out 1. Okay, so your typical function for your natural log has the vertical asymptote at 0, and then it has the x-intercept at 1. And so if you were to just look at these first 3 examples, they're just some transformations. Like here it's shifted to the right 2. So now the asymptote, instead of it being at 0, is at 2. The intercept, instead of it being at 1, is at 3. And then there you have it. You have that graph. Here we've got a vertical shift. So the vertical shift doesn't change the asymptote, but it takes that x-intercept, shifts it up 1. So that means this new x-intercept is going to be to the left of where it initially was. And then the example C, you have the vertical stretch times 2, which it won't move the important features. The asymptote is in the same spot. The intercept is in the same spot. It's just going to be steeper as it goes up, and then of course steeper as it goes down. The vertical stretch doesn't really do a whole lot to us. It's mostly the horizontal shifts, the things that change where those critical features are, like asymptotes and intercepts. Those are the transformations we care the most about. All right, so I think that's pretty good. Again, you could always pause the video, and if you need to, go Khan Academy some stuff for exponentials and logs. But we're going to just do a little bit more review, and then we'll get into the calculus. So I guess to start off, let me zoom it out a little bit so we can get it all on the screen. We have the two different forms of an equation. You have the logarithmic form of an equation, and then you have the exponential form of an equation, and you can always switch from one to the other. So if you have something like log base b of x equals a, if you wanted to rewrite it from a log into an exponent, you would follow this circular pattern. You would do a base b to the a power, and that would be equal to x. All right, what the log is equal to, so this thing that's by itself, that's the exponent on the exponential, right? Logs are exponents. Hopefully you had a previous teacher tell you that at some point in your past. But you can switch it from this logarithmic form into the exponential form, b to the a power equals x, right? It's kind of this circular pattern. And vice versa. If I started with a log and I wanted to rewrite it as, if I started with an exponential and I wanted to rewrite it as a log, you would do a log base b of x, and that would be equal to a. So again, that circular motion will kind of hold true. B to the a power equals x. Right? That's how you would switch it from a log to an exponential, or you would do a log base b of x, and it would be equal to a. There's always kind of that circular motion for how you can switch from one form to the next. Now we have some basic facts. ln of 1 is 0. The reason why is because b to the 0 power for any base, I guess that should be b, right? Any number that you plug in, really any base, anything to the 0 power is going to be 1. So e, I guess since that's a log, it should probably be e to the 0 power, not b to the 0 power. But it would really work for anything, like log of any base, log of 1 is going to equal 0 because any base to the 0 power is going to give you 1. Okay, so that's really nice. Then we have the ln of e is 1. The reason why that's true is because if you were to switch this and rewrite it as an exponential, so you're thinking, hey, that's log base e, right? Your natural log, that's log base e. That's e is called the common. E is called the natural base. So instead of writing log base e, they have ln, which is our natural log. Log base 10 is the common log, so frequently you won't see the 10 written. If you just see a regular log, it's base 10. If you see the natural log, it's base e, which is our natural base. So if I have something like ln of 1 equals 0, it's because, hey, remember, that's log base e to the 0 power equals 1, right? That's easy, right? Or you're thinking e to the what power would give you 1. Well, that what power would have to be 0. And then here for the next one, ln of e equals 1, because remember, that's log base e to the what power would equal e? Well, e to the first power would equal e. So some two facts that you would need to remember. ln of 1 is 0. That's where you have the x-intercept, right? When x is 1, the y value is 0. And then when the x value is e, the y value is 1. So ln of 1 is 0. ln of e is 1. Okay, some basic facts. And then we have some properties of natural logs, and these are pretty important, so hopefully you have them in your wheelhouse from a previous year. And here's basically what they are going to do for us. We can either expand or contract logs. If here I take the properties 3 and 4 kind of go together, and then 5 is by itself. But if I have multiplication inside of the log, right, so that's a times b in the argument, I could take that thing and I could split it up, and I could have ln of a plus ln of b. Or if you have the division inside of the log, you could split it up, and you would have the ln of a, because that was on the numerator, the positive exponent, and then minus ln of b. Since the b was in the denominator, it would have a negative exponent, and so everything that's in the bottom, the log of that chunk would need to be subtracted. And that works, both of those work both ways. So I could go from multiplication inside to having addition between the multiple logs, or if I saw that I had addition between these multiple logs, addition between multiple chunks would combine into multiplication inside. Or vice versa for this other one as well. If you have division inside, it's subtraction between the multiple chunks. Remember, the stuff that's on the bottom, that's what's the negative, that's what's being subtracted. Or if you have the subtraction, you could combine it into the division inside. Those properties work both ways. Same with this one. If I have an exponent, now that is an exponent in the argument, right? It's an exponent on the stuff that's in the argument. There's another bell. How wonderful. What you could do is take this exponent and you could bring it down to the front. And instead of having an exponent in the argument, you could just have a coefficient of that log. And vice versa. If you have this coefficient out in the front, you could stick it as an exponent inside. Okay, so we have the properties of expanding and contracting logs. We also have that property how if you have an exponent, you can move it down, or if you have a coefficient, you could stick it up. Those are really great. Let's just do a little bit of practicing, and then we'll get into the calculus for today. Okay, it says write as a sum, a difference, or a multiple of logs. So it gives us this really nasty natural log, and it's going to want us to split it up, right? That log has all been combined into one chunk. By the way, these properties work for other things besides ln, right? Ln is log base e. Those properties work for other bases as well. They would work for log base 10s, log base 7s, whatever. Multiplication inside is addition between the chunks. Division inside is subtraction between the chunks, or vice versa. Addition combines into multiplication. Subtraction combines into division. And of course, we have the coefficient and the exponent rule. So here we're going to take this chunk and we're going to split it up. And we're going to expand it. So instead of it just being one nasty big conglomerated log, we're going to split it up and have the individual chunks. So here's all this stuff that's inside. Clearly I've got some multiplication, this chunk times itself. You also have a cube root in that denominator. We're going to split it up. So I'm going to have this chunk, which is on top. So I'll have ln of x squared plus 3. That was on the top. That one was on the bottom. So we'll do minus ln. Then I have the cube root of x squared plus 1. Kind of getting out of... I shouldn't have made so much room on that one. Oh well. And now we're still not done because we could simplify it a little bit. We took the division. We split it up into the subtraction. The stuff that was on the bottom, of course, that's the one that's being subtracted. Now the only thing else you could do is take the 2 and bring it to the front. So we could have 2 ln of x squared plus 3. And I could take this cube root, which is a 1/3 power, and I could bring that 1/3 to the front. And then something like this is about as simple as we could get it, right? We could expand it and we could write it as a sum or difference. This was a difference since it was subtraction of the multiple logs. Okay, so that was really nice. We expanded it. It would work both ways. So if I had something like this, I could combine it into the one log, and that's what the next example is going to want us to do. Here I could take this 2, and I could stick it as an exponent. I could take this 1/2 power, which means square root, and I could write that as an exponent. And then since I have addition between those two logs, I could combine it, right? And when it combines, there's going to be multiplication inside. So I would have this chunk, which is x plus 3 squared, and then I would also have the multiplication times this other chunk. So times the square root of x minus 2. Okay, most of the time we expand stuff, right? Because we don't like having it all combined, because then the chain rule would get really, really, really nasty. Like taking the derivative of something like this would be awful, because you would have quotient rule, and then you would have chain rule everywhere, and that wouldn't be fun. However, if you were to split it up, taking the derivatives of these individual pieces would be much easier. So usually we would do stuff like this where we expand it, but if you ever need to contract them and write them all as a singular log, we could. Now, important note just really quickly, and then we'll move on. You can't do anything with this, right? The property tells me that, hey, that exponent has to be affecting the whole entire argument. So here, since it's x squared and then plus 3, that 2 cannot come to the front. Similarly, this 2 cannot come to the front. If you had something like that 2 affecting this whole chunk, well, that thing could come to the front. But since that squared exponent is only affecting that singular term and not the whole argument, this one could not come any farther out to the front. So Just kind of be careful with that. But if you know the properties, I think you should be pretty good. Again, I don't remember if you guys did this in a slide deck or if you did it actually in a pre-calc class last year. Or if you remember all the way back to Algebra 2, you should have done the exponentials and logs in Algebra 2. Just some basic properties we're reviewing here. Okay, now let's do these last two examples, and then we'll get into the calculus, which will be the new stuff for today. All this pre-calc stuff, in theory, should be reviewed. Okay, so it says use the property of logarithms in the facts that ln of 2 is this weird ugly decimal 0.6931 and ln of 3 is this uglier decimal 1.0986. Use those two facts to find the approximation value of ln of 12 and then ln of the root of 2. So basically what we want to do is take this more complicated number 12 and we want to break it down into somehow 2's and 3's because I know information about the ln of 2 and the ln of 3. Now yes, you could just type this into your calculator, but if you didn't have a calculator, you'd have to somehow figure out how can I use the two pieces that it gave me, which is the ln of 2 and the ln of 3. So how could I rewrite 12 in terms of 2 and 3? Well, I know there's a couple ways you could do this, but I'm just going to demonstrate one. I know 12, you could rewrite it. Oops, not 4 times 2. I could rewrite 12 as 4 times 3. And then I could split this up. Since it's multiplication on the inside, I could split it up. So we could have ln of 4 plus ln of 3. Now that chunk I'm pretty much done, right? Because that chunk I know what it is. That's great. And then the ln of 4, I'm not quite done yet, right? I need to do a little bit more. So what you could do is, 4 is 2 times 2, right? So that's 2 times 2 inside there. So you could do ln of 2 plus ln of 2. Right? This chunk right here is the expansion of the ln of 4. Then, of course, we had the plus ln of 3. And now, look, everything is in terms of 2 and 3, right? Instead of doing 4 times 3, if you wanted to, you could have just done 2 times 2 times 3, and then that will just take you to that right answer. And then you would just have to plug in what those terms are, and then you would be able to get that this answer is 2.4848. Okay, I skipped a step, but you'd plug in this number here and here, you'd plug in this number here, and then you'd end up getting the 2.4848. That's one way of doing it. Or if you didn't want to do 2 times 2 times 3, you could have done 2 squared times 3. Now the 2 squared, you could have rewritten it as 2 ln of 2. Right? Instead of having ln of 2 plus ln of 2, instead of having the 2 times 2, you could have had 2 squared. And so when you split it up, that 2 could have come to the front. So you could have had 2 ln of 2 plus the ln of 3. But that would also, I don't know why I put 2 equal signs. This would also give you to the same thing. Instead of adding those things twice, you could just have it once and then multiply it by 2 and then the ln of 3. They would both work, right? A couple different ways to do it, but the idea is to take the 12 and break it down into chunks using 2's and 3's because we were given pieces of information about the 2's and 3's. Same thing for the last one. This one's a little bit easier because there's only one way to do it, right? Square root of 2, you could rewrite that as 2 to the 1/2 power, and then that 1/2 power, you could bring it out to the front, so you can have a 1/2 ln of 2. You would just then plug in this number, right, the value that it gave us, and then we would end up getting 0.34655. So the idea is that when I have a log equation, if I have something that's a little bit more complicated, if you're given two smaller, simpler pieces of information, you just have to figure out how can I use those log properties to split up this more complicated thing and to get it in terms of the things you know about, right? How could I get the 12 in terms of 2's and 3's? How could I get the square root of 2 in terms of just the 2's and 3's using just those properties? Okay, hopefully that helps. Now let's go ahead and get into the calculus, which is for today. How do I take the derivative of a natural log function? And it's really very easy. For the parent function, if I have ln of x, the derivative is just 1 over x. So that's really nice. There's my parent function. That is something you're going to want to know. The derivative of ln of x is 1 over x. Okay, so if I have ln of stuff, right, this just says ln of u, so that u means I'm going to have to do chain rule because it's just some inside stuff. The derivative of ln of stuff, well, whatever's inside of that log, whatever this argument is, it's going to go to the bottom. And then du dx, that's just telling you to do chain rule. So typically how I write it, if I have, ddx, if I have the ln of whatever, Okay, whatever that thing is, whatever's inside of the log, that goes to the bottom. And then your chain rule derivative, the derivative of that stuff, I typically will put it on the top. Okay, that's the rule for how I can take the derivative of a natural log. Whatever's inside of the log goes to the bottom. The chain rule derivative of that stuff goes to the top. Let's practice. This is an easy derivative. Let's practice. I've got ln of 2x. So whatever's inside of the log is going to go to the bottom. Chain rule derivative, hey, what was that inside piece? Oh, the derivative of that's not 1, so you would have to do chain rule. The derivative of that inside piece is 2. So I have 2 over 2x, which will reduce into 1 over x. Okay, let's do a little parallel example. What if I had ln of 5x? Well, whatever's inside of the log would go to the bottom. The chain rule derivative would go to the top. And look, you would still end up getting that same 1 over x. Or what if we had something just even slightly different still? What if I had something like the ln of negative 8x? What if we threw a negative in there? Okay, well, whatever's inside of the log would go to the bottom. The chain rule derivative of this piece would go to the top, and then look, the negatives would cancel, the 8s would cancel, and you would still end up with just the 1 over x. In general, if I have ln of, we could say bx, where b is any constant, any number, positive, negative, big, small, whole number, fraction, it doesn't matter. If this is just some number, the derivative of it will still just be the 1 over x. Whatever's inside of the log goes to the bottom. Chain rule derivative of that stuff that was inside, chain rule derivative goes to the top. But if that was just like some linear term, right, it's always just going to end up simplifying to 1 over x. Okay, let's just plow through a lot of these examples, and then we'll try to finish this. Yeah, we got 2 more pages. I think we'll be okay. Alrighty, here we go. Natural log of x squared plus 1. Whatever's inside of the log, I always just copy it. Whatever's inside of the log goes to the bottom. Chain rule derivative. Don't forget to do the chain rule. Chain rule derivative goes to the top. That's it. Do not reduce an x. That would be breaking the laws of algebra. Don't do it. I know it's tempting. Don't do it. Whatever's inside of the log goes to the bottom. Chain rule goes to the top. You're done. Now here I have a product rule. So I'm going to need the derivative of the first times the second, plus I need the derivative of the second. The derivative of ln of x is 1 over x times the first. So I've done my product rule. 1 times the ln of x is just the ln of x. And then here the x on the bottom, the x on the top, those would reduce. And here I'd end up getting ln of x, and then separately that chunk that's a plus 1. So product rule will still apply. Now, this one, you would probably want to be a little bit careful. This one, you could take the derivative right away, and you could just brute force it. But it's a lot easier if you remember that a square root is just a 1/2 power. And then, hey, since I have that exponent on the argument, that exponent, you could actually bring it down to the front. And this original function, without having done any calculus at all, this original function, you could just algebraically rewrite it as 1/2 ln of x plus 1. Instead of having that exponent, you could have a coefficient. So here we go. The coefficient, I'm just going to copy it down. Whatever's inside of the log goes to the bottom. Chain rule derivative goes to the top. Oh, the derivative of this piece, the derivative that's 1, the derivative that's 0, so the derivative is just 1. So you don't really have to worry about chain rule there, since it was just 1. And then I would end up getting 1 over 2 and then x plus 1. If you want to distribute it, that's fine. But it's a lot easier, instead of having that square root, to rewrite that as a 1/2 power and then to bring it to the front. That's a lot easier. Do you have to do it that way? No. Okay, so here's how you could have done it differently. If I wanted to leave it as ln of square root of stuff. Remember your power rule. If I have x to the 1/2 power, the derivative would be 1/2 x to the negative 1/2. So then it would be a 1 over 2 roots of x. There's your derivative formula. Anytime I've got a square root of something, it's always going to be 1 over 2 square roots, right? If I've got square root of stuff, it's always going to be 1 over 2 square roots of stuff. Whatever's inside will still be inside, and then you would just put the chain rule derivative on top, right? It's just a power rule that we've been doing since probably October, and then hopefully, I guess probably maybe November. So that one is just something that you should know by now. So if you wanted to just brute force this thing, right, since I have the square root inside, you would have to do chain rule, but we know how to take the derivative of a square root, right? Here's what it would look like. Whatever's inside of the log would go to the bottom. Now, instead of doing all the chain rule on the top, I'm just going to do the chain rule on the right. So ln of stuff, right? This is a composite. You have ln of stuff, then you have what that stuff is. The derivative of ln of stuff is right here. It's 1 over stuff. But now I need to account for what that thing is. And the derivative of a square root would be 1 over 2 of the roots. And then look, the 2 is still there. The square root of that thing times the square root of that thing. That would end up giving you the same answer. It's just a lot easier to, instead of doing the chain rule with the exponent on that stuff, it's a lot easier to bring it to the front and just have a coefficient, right? You can do it either way, but it's just easier to avoid that chain rule, I think. Just my advice. If you have some exponent inside, bring it to the front. Your life would be a lot easier. Okay, here we've got ln of ln. So this is another composite. Your outer function is ln of something. The inside piece is also ln of x, right? So we have to do both layers. The derivative of ln of something is going to be 1 over whatever that thing is. So whatever's inside of the log goes to the bottom. And then you would need to do the chain rule derivative, right? Now I've accounted for that layer. Now I need to do the derivative of this. So you could either put 1 over x on the top, or you could just do times 1 over x also on the bottom. That would be fine. Or if you wanted to, you could rewrite it like this. Whatever's inside of the log goes to the bottom. Chain rule derivative of that inside piece would also have to be accounted for, and the derivative of this ln of x would be 1 over x. So you could have had 1 over x on the top, or you could have the 1 over x on the right, or if you wanted to, you could just combine them and have x ln of x on the bottom. Lots of different ways that the answer could look. Now this one, you don't really have any options. These two, the last two on this page, are kind of similar, except this one's ln of x cubed, and then that one's ln of x cubed. Okay, so this one's different. This one's a composite where it's something cubed, and then the inside piece is ln of x. This is ln of something, and then the inside piece is x cubed. So while they look similar, right, be careful. Your order of operations tell us that those parentheses coming before the exponent make a big difference, right? Remember your PEMDAS. So when I take the two derivatives, you have to make sure you're identifying the composite correctly. Here, if I have something to the third power, the derivative would be 3 something squared. Whatever was inside getting raised to the third, that same thing is inside getting raised to the second. So that layer's done. Now I would have to account for that inner piece. And so you could just leave it like this. Okay, so that would be fine. And then here, this next one, since I have ln of stuff, right, this outer layer, whatever's inside of the log could go to the bottom. And then you can either do the chain rule derivative over here on the right, or if you wanted to, you could think whatever's inside of the log goes to the bottom, chain rule derivative goes to the top. The ln of piece is accounted for with this part of the derivative. The x cubed is accounted for with that part. Again, you can either write the chain rule on the right, or you can just put it on the top. But here you're going to have some x's that cancel. So you'd end up with this thing that's just 3 over x. Okay, now for this last example, you could have used your properties to rewrite it first. Okay, because this ln of x cubed, since that cube was on the term in the log, you could have brought this 3 out to the front. And this original function could have just been rewritten as 3 ln of x. So this 3 would have just been a coefficient. The derivative of ln of x is 1 over x. And then look, you would still end up with the same thing. So the better you know those log properties and the easier they are to recognize for you, kind of a lot of these questions may become a little bit simpler. This one, you could not have brought that 3 to the front, all right? When I took the derivative, it comes to the front because of the power rule. But algebraically, you cannot move this to the front because it has to be inside the argument. It has to be attached to that whole entire argument. And if you do have that situation, then you could bring it to the front using that property of logarithms. Okay, so we got one more page, and then hopefully my voice doesn't give out. We'll see. Okay, one more page, and then we'll end this video. It says, write the equation of the tangent line to the graph. Ooh, here we go. It's been a while. Equation of a tangent line. Y minus y1 equals m. X minus x1, right? That's great. It gives me the function. It gives me the points. How lovely. Let's plug in the stuff we know. It's going to be y minus 0. I don't know the m yet. That's going to have to come from the derivative, but then we'll have x minus 1. So remember, that's your m value. That's the slope of the graph at that specific point. So I'm going to have to take the derivative and then plug in. So here we go. ln of x to the third power. We just did it, right? We just did this a second ago. The derivative, we literally just did it, is 3 over x. So therefore, the derivative, plug in the x value. The derivative when x equals 1 is going to be 3. So then the slope of the graph at that point, which is the slope of the tangent line to the graph at that point, is just 3. And if you wanted to distribute it, you could y equals 3x minus 3, or you could just rewrite it as x minus 1. It's like, all those are fine, but typically you're just going to leave it in point slope form unless it tells you otherwise. Okay, next one, same type of question. Write the equation of the tangent line. So we've got y, minus negative 1, so it'll be y plus 1. We'll have to get the slope from the derivative, and then x minus 1 once again. So now I'm just going to have to take the derivative, and then now I'll plug in 1. So here we go. I have 5 ln of x. 5 is just a coefficient. The derivative of this is 1 over x. So the derivative of 5 ln of x is going to be just 5 over x. Then the derivative of this is minus 3x squared. So then you would just plug in 1. 5 over 1 is 5. All that's just going to be 3. So it looks like that value is 2. Okay, so equations of tangent lines, remember you have point slope form. Y minus y1 equals mx minus x1. If for some reason it only gave me x equals 1, if it only gives you the x value, that's okay. You would plug the x into the original. That's how you would get the y value. You'd plug the x into the derivative. That's how you get the m value. Okay, next one. 4 more examples, and then we'll be done with this video. Hooray! Here we have this function, which is defined by an integral. And then remember, it's starting with t's, and I see I've got the x's up in that limit of the integration. And it says, here's f, find f prime. So I know to go from f to f prime, it would want you to take the derivative. So it would want you to take the derivative of this stuff. 2t plus 7 dt. Right? That's how you would get from f to f prime, is you take the derivative. But we just learned the second FTC not too long ago. Right? Second FTC, that tells me that when I take the derivative of an integral, they're going to cancel. And remember, this constant doesn't matter at all. Your function starts in terms of t. It's going to end in terms of x. So instead of it being 2t plus 7, you're going to have 2 something plus 7, right? There's my function. But then instead of t's, whatever this chunk is, you're going to plug it in. So I'm going to have 2 ln of 5x plus 7. That's great. And then you would have to do chain rule, because the derivative of this piece is not 1. The derivative of this piece would be 5 over 5x, which is 1 over x. So then you would need to account for that chain rule, right? And so here we have 2 ln of 5x plus 7, and then you could either leave the 1 over x at the back or at the front. It doesn't matter, right? A couple different ways of writing the exact same thing. But the trick with this question was second FTC. Taking the derivative of the integral cancels. The constant doesn't matter. So all I had to do was take this chunk, plug it in where I saw the t, and then of course, since the derivative of that piece that I plugged in is not 1, you had to do chain rule. And remember, if that order for the integration had been flipped, all you would need is a negative out in front. Second FTC are designed to be quick and easy questions. Just don't overthink them. Okay, here it says an implicit defined equation. We have x cubed plus 2 ln of y plus y cubed equals 4. Find dy dx. It's been a while since we've done implicit, so I like doing all this. We did all the stuff first semester with just algebraics and the basic trig functions, but now once we're doing these transcendentals, it kind of gives us an opportunity to bring these topics back, like implicit differentiation. How do I take the derivatives where there's x's and y's? So you just do chain rule when the variables don't match. Here we go. We're going to find the derivative with respect to x. So here we go. The derivative of x cubed is 3x squared. Now the derivative of ln of y is going to be 1 over y. So I have 2, that's just a coefficient, and then this would just be 1 over y. So here I'm just going to rewrite that as 2 over y. The 2 because of the coefficient, and then whatever is inside the log goes to the bottom. But then, of course, since that one's defined by y, and you're trying to take the derivative with x, since that chunk has y's and you're doing the derivative with x, you need to do y prime. Or if you don't like y prime, you can do dy dx. But the derivative of ln of 2ln of y would be 2 over y and then y prime. The next chunk, since I have y cubed, it would be 3y squared times y prime. The derivative of 4 is 0. And then what we would be doing is trying to get the y prime by itself. So here, the non-derivative term, I would move it over. So I'd have 2 over y prime, plus 3y squared. Y prime equals negative 3x squared. Then I would need to factor that thing out. So I have 2 over y plus 3y squared. And then I would need to divide by this chunk in the parentheses. So here I'd get y prime is equal to negative 3x squared over 2 over y plus 3y squared. And that would be a perfectly fine answer. If this was a multiple choice question, which it very likely would be, I would guarantee you that it's not going to look like that because they don't like having a fraction within the fraction. Okay, so what we could do is we could just multiply everything by y. So this one we could rewrite it as negative 3x squared y over 2 plus 3y cubed. We basically multiplied it by 1. But if I multiply by y on the top and y on the bottom, right, that's just multiplying it by 1 overall. It doesn't change the value. It just changes how it looks. So if I multiply this chunk by y, if I multiply this chunk by y, multiply that chunk, as long as I multiply everything by y, the top and the bottom, right, I'm multiplying by 1 overall, this is equivalent to this, but that just looks a little bit nicer. Okay. And then the last two, here we go. It says show whether or not y equals 3ln of x plus 4 is a solution to this differential equation. And it says x, y double prime. Sorry, that got a little bit kind of crowded. That's x, y double prime plus y prime equals 0. Now, if you ever have an example or a question right here where it says determine whether something is a solution or not. Well, a solution means when you plug it in, it works, right? That's what it means, right? Like if you have the function y equals 5x, well, the point 2, 10 would be a solution because if I plug in 2 for x and I plug in 10 for the y, 10 would be equal to 5 times 2, right? If you plug it in, it works. That's what it means for something to be a solution. So here what I'm going to have to do is I'm going to have to find the second derivative, plug it in. I'm going to have to find the first derivative, plug it in. I'm going to try to see, hey, when I plug all that stuff in, does the equation work? If it does, then yes, it would be a solution to that specific differential equation. If I plug in all the stuff and for some reason the left side doesn't equal the right side, then the answer would be no, it's not a solution because when I plugged it in, it didn't work. So let's go for it. We need the first derivative and the second derivative, then we're going to plug some stuff in. So let's go take those two derivatives first. Now the derivative of 3 ln of x is just 3 over x. The derivative of 4 is 0. Okay, so that's nice. If you need to, that's just a power term. Right, 3 and then x to the negative first. I need the second derivative also. That negative 1 would multiply to the front, so I'd have negative 3x to the negative second power, so I'd have negative 3 over x squared. So I've got the first two derivatives. Now let's just go into this differential equation. Let's plug them in. It's x. Then I need the second derivative, so we'll plug it in. And then plus, then I would need the first derivative, so we're going to plug it in. And we're going to see, does that equal to 0? If the answer to this is yes, then yeah, it is a solution. If for some reason this doesn't equal 0, then the answer would be no. Okay, so let's cancel one thing at a time. The x will cancel one of those. And we're trying to see, does this still equal 0? Oh, and then now I got it, right? Those two things, because of the additive inverse property, yes. Those two things do equal each other. So we would say yes, right? This function y is a solution to the differential equation. Because when I take this and I plug in all the corresponding parts, that differential equation works, right? The left side equals the right side. When I plug it in, it works. That means yes, it is a solution. Okay, if I got something that it wouldn't have worked, then the answer would have been no, it's not a solution. Okay, but if it asks you, is something a solution or not, it means when you plug it in, does it work? All right, last one. It says, show that y equals x ln of x minus 4x. Show that that function is a solution. Okay, so notice the difference in the terminology in between this example and the previous one. On the last question, it says determine or show whether or not it works. This one's telling you it's going to work, right? And it's telling you show that it works. Okay, so this one had the option to somehow not be equal, right? Because it says show whether or not. So it possibly could have not worked. When I take this derivative and when I take everything and I plug it in, it had better work. Because this question's not asking, does it work or not? It tells you that it works. And it's just wanting you to show the steps to prove that it works. So just be careful. Sometimes your reading comprehension skills can kind of tip you off. This one could have worked or it could have not. This one's going to work. So if for some reason you were to get something at the end where the left side doesn't equal the right side, something would be very wrong. Okay, because it's not going to fail here. It tells us it's going to work. We just have to show that it is a solution. And now here I need x, which is just x. I need the y, which I have already. So all I need is the first derivative. On the last question, we needed the second derivative, so we took the derivative twice. Here I only need the first derivative. Now this is going to be your product rule. We did it earlier. The derivative of the first is 1 times the second. And then it'll be plus the derivative of the second times the first. And then the derivative of minus 4x would be minus 4. So here, this first derivative, we end up getting ln of x minus 3. Okay, right here you still had the product rule. That's what it expands out to. We did it on the first page. Go back and rewatch the video if you need to. And then here, let's just plug everything in. So it says x plus, now I need the y equals. So here we go. Let's plug it in. X ln of x minus 4x. So I got the x. I plugged in the original function for y. Minus x times, now I need to plug in the y prime, so that was ln of x minus 3. And then we are trying to see that it equals 0. Now this one's not a question mark because we're not trying to determine if it is 0. Like it's going to be equal to 0. We just have to show all the steps. All right, so let's distribute this negative in the x. So we've got x plus x ln of x minus 4x. Then that's going to be minus x ln of x minus negative, so plus 3x. We got to just cancel one thing at a time. So here we go. Let's cancel those. So you have the positive and the negative, and then those you could look. All those are common terms. Well, let's just rewrite them. I'm going to combine those two really quickly, right? The positive 1 and the positive 3. So I've got a 4x minus 4x, and then yes, right? That does work. 0 equals 0. Yes, right? But you'd want to show all the steps. And kind of conclude and verify that yes, when I plug in everything does cancel, but you have to show everything canceling just one at a time, right? We know it kind of tells us, yes, it's going to work, but you can't just do something like this. Oh, yep, it works, right? You can't just cross it all off because you're told that it's going to work. You have to show one step at a time that it works. Like distribute some stuff. Okay, then there's one thing that cancels. Then you could combine, right? Then you have the next things that cancel. Don't just cross it all off and be like, all right, I'm done. There it is. That's not showing. That's just being lazy. Okay, so just be careful. Determining whether something is a solution or not means does it work when you plug it in? When you plug it in, does the left side equal the right side? This last example, it wasn't asking, does it work? It told you it's going to work. And then you just had to show the steps. Okay, in the next video, we'll work with some of the integrations involving the natural logs.